So given how critical a database is to a system and how it is the most brittle component of your architecture, it's very important that your database scales to the requirements of your system. Right? Now in this one, let's talk about how or different strategies to scale a particular database. Now, the strategies that we discuss are not just limited to relational database. You can apply to non-relational DBs as well. The strategies are very common and very general way to scale any stateful things like database. Right? Okay. The first one is vertical scaling. When you talk about vertical scaling, a database is all about adding more CPU, more RAM, more disk to the database. Now what happens is when, let's say you are starting out, you just build an early version of your product, you said, hey, 4 GB RAM is more than enough for me to perform, like to store all the data that I have. But when you see progress, when you see huge amount of load coming in, that 4 GB RAM does not seem enough. So that is where for you to be able to handle a huge amount of load, you would have to pour in more resources into that database. So which is mean that you add more CPU, more RAM, more disk to the database and make it big enough to handle the load, right? So this, when you do this, when you upgrade your database, so typically in today's day and age, most of our infrastructure is on cloud, which means that you typically don't have to deal with all the ugliness that comes into copying data and whatnot. Almost all cloud providers, Azure, GCP, AWS, they give you one-click solution to upgrade your database, right? So what I would recommend is take that as a black box, right? Take that as something that, hey, you just need to do 2 clicks to upgrade your database to a higher infrastructure level. So from 4 GB RAM to, let's say, 8 GB RAM. So when you do this, although your cloud provider abstracts out all the complexities of it, but it would still require a downtime because a database would reboot at that time. So whenever you are scaling up vertically, there is a short duration of time where database would be unavailable, which means your system would have a small downtime. But it does give you ability to handle quote unquote scale or more load that you are receiving, right? So in most cases, it is just 2 or 3 clicks away and you would be able to vertically scale your database. Now here, one key thing to note is whatever you are scaling vertically, it has a limit. Even when you go to any cloud console, AWS, GCP, Azure, you would see that, hey, only up until a certain point, the options are there. You cannot go beyond that, right? Because vertical scaling has a physical limit. I'll give a small example for that. Let's say you purchased a phone, right? A smartphone. That smartphone comes with an expandable storage. Now that expandable storage you get this option that, hey, you can put at max 128 GB expandable storage. Now what happens when you put in 1 terabyte there, right? 1 terabyte SD card in that, right? It does not recognize it, right? Because of physical limitation. If I want to go deeper into computer architecture, that is where your cache lines, bus ratios, and all of these details come in, right? So there is an actual hardware integrated circuit level limitation because of which you cannot go beyond a certain level, which is why people say vertical scaling has a limit, right? So if vertical scaling has and it does not mean that you should not do vertical scale and only horizontal scale. Vertical scale is very easy, 2 clicks, one small downtime, you have your database up and running, like you have your database upgraded to handle more load. Unnecessary complications of horizontal scaling you can avoid to most extent. But if your data is huge, humongous, the amount of load you are handling is humongous, that's where you have to think of horizontal scaling. Now, another way of scaling it, first we talk about vertical scaling. Now, instead of doing vertical scaling, let's do horizontal scaling. In that, first one we'll talk about is read replicas. Now, read replicas is a very standard way to scale the reads. In most workloads around the world, around the products, across the company, you would always see a very high read to write ratio, which means if there are 90 for every 100 operations that are happening on the database, 90 are reads and only 10 are writes, right? So there is a huge difference in read to write ratio, which means that what we need is, if there is a lot of reads request coming in, what if we put all the read request onto something called as a read replica, while my other database is handling all the writes. This way, I'm not just having one database which is handling both reads and writes. I'm just moving my reads to another database. This way, what we do is we scale our reads independently. This is a concept of read replica. Now what happens over here is you move reads to another database. But now, how do you call, like how do you know that reads need to go to read replica and writes need to go to master? By the way, I did not add the term master. So when you add a read replica, one database becomes the master database, which takes up all the writes, while the other database becomes read replica or slave. I don't prefer the term slave. Read replica or follower, whose job is to follow whatever write has happened on the master. That happens through replication, which we'll take a look in 5 minutes. Right? But with this structure in place, with master and replica in place, what happens is master is free to handle as many write requests as are coming in, while all the reads are handled by read replicas. Now the next question comes in that, hey, if now I have two databases, how would I know that reads need to go to replica while writes need to go to master? How would we know that? This is where a very simple way to do this is do it at your API server level. So in your APIs that you write, you create a database connection object. The database connection object that you create can create connection with, you typically create connection with one database. Instead of creating one connection, you create another connection with another database. So instead of having one connection object, you have two connection objects, one with master, one with replica. Now, depending on what your read is, what your write is, in your business logic that you're writing, you pick the connection object on which you'd want to fire the query. So if you'd want to fire a query, it's a read query, you can know that it can go to read replica. Just use the connection object of the read replica to query it. As simple as that. As simple as that, right? And when you're doing it on master, or when you know that this is a write operation and I want to do it on master, you use the connection object of the master. So what I would recommend, implement a very quick prototype of horizontal scaling using read replicas. Have your simple API server making calls on two different databases, right? Have two different APIs that does that. You know how easy it is to just put your request to either master or read replica. A lot of folks think it is automatically happening. No, it's not automatically happening. A simplest way to implement is let your API server decide where to send the request to, either to read replica or to master. You just create objects around it and pick one over other, right? Okay. Now, we know that master and replica are connected via quote unquote replication. So this replication determines how writes from master go to replica. Now there are two modes of replication. First is synchronous replication. Second is asynchronous replication. Now we'll talk about synchronous replication first. In synchronous replication, what happens is when your write comes to your API server, your API server pushes or makes the write to the database. Now the write has happened on the database. Now here in synchronous replication, the writes from the master goes to replica, right? So either your master makes a call to replica or API server makes a call to replica, irrespective. But the idea is that your API server does not respond back to the client unless the write has happened on the master and on the replica. Then only we would say that write is successful, and then only we would return it to the user that, hey, write is done. This way, your master and your replica will always be in perfect sync. There will always be a very strong consistency between these database, because you are not terminating your write until your write is also written or your write is done on the replica, and then only you are saying that, hey, now I'll return it to the user. So this is obviously very slow because it would increase the latency that user observes, because now user does not have to just write, like the API server does not have to just write to the one database and return. The writes have to go to two databases now, right? So you would see a slightly higher latency, but what you get you get almost zero replication lag, because writes are going on both sides and then on both databases and then only being returned to the user, which means that there is zero replication lag between the two database, but your writes are slow. You can't help, right? It's entire world is a trade-off. Entire domain of computer science is trade-off. So we are trading off strong consistency and replication lag, right? Okay. Second mode of replication, which is very common in day-to-day world, almost all databases follow this, is asynchronous replication. In asynchronous replication, what happens is the write coming into API server is written onto master, and then the response is taken by API server and sent back to the user, right? So there is no waiting that needs to be, the master does not have to write to replica immediately. So what happens over here is your write typically goes to master and sent back to the user, done and dusted. So user sees very fast writes. It does not have to wait for the write to propagate to replica yet. So now how does replica get the updates from the master? Which is where what happens is almost all databases come up with a way to create replicas. MySQL, Postgres, MongoDB, everyone has a replica. So what you do, you create a small configuration. It's a small configuration that you enable that, hey, this database is a replica while this database is master. So you specify that, hey, this replica is following this master. So what happens is replica periodically pulls the data from the master. It knows up until this point, it has the data. It periodically checks with the master and says, hey, what's next after this? So master sends all the queries that have been fired after that, and it sends to replica. Replica applies those things on that, right, on itself. And this way, instead of master pushing the data to the replica pulls it periodically from the master. Now here you can see that there might be some delay after which a replica is pulling it from the master. So which means that there is no strong consistency between this database. So there would be a chance where your write has happened on the master, but before it has gone to replica, you make a read on the replica. There are other challenges that comes with it, right? So the write would have still not been there on replica, but it would be there in master. So the databases are not in perfect sync. This is replica lag that we are talking about, right? So these are two very common ways of doing replication, synchronous and asynchronous. Asynchronous replication is what we all configure in day-to-day world. We all configure MySQL, Postgres, MongoDB, Redis. Pick your favorite database. Almost every single database supports read replica, and this is how almost all of them do replication. It's all asynchronous, but there are places where synchronous replication is also very helpful, especially when you need strong consistency between master and replica. When I say consistency, it's more about having almost zero replication lag between master and replica. Right. Now, the next way to do horizontal scaling is sharding. Now, sharding is very interesting. So now here what we did is we scaled the reads. Now we can add many read replicas reading from the master, and we have been able to scale the reads. But now what if we get huge amount of writes? What if reads are okay? We scale the reads, but now we are seeing enough writes. We say, hey, we do vertical scaling, but after a certain point, you cannot do vertical scaling. What if you want to go beyond that? Which is where sharding comes in. So what sharding suggests, and I'll give a brief intro to sharding at the moment, then we'll go deeper into sharding in the next one. So sharding is all about, because your one node cannot handle the data or the incoming load, write load, we split it into exclusive subsets of data, right? So for example, what we do is instead of having one data node holding all the data, you have 3 nodes containing 3 subsets of data, mutually exclusive subset of data. I'll give a simple example. Let's say I have a key value database in which I'm storing keys where that starts with A to Z. So what I can do is I can have A to J over here, K to T over here, and T to Z over here. I can define my own logic that, hey, all the keys that are in A to J range, they would all go over here. From J to T will go over here, and from T to Z, from U to Z will go over here. This way what we are doing is we are creating 3 mutually exclusive subsets of data, and each shard is responsible for its own thing, right? This is sharding. Now, similar to how your API knows about read replica and master, here Your API, the simplest implementation says that your API knows about existence of all the three shards and it knows where to go to. It knows that API server has the logic that if the key is in range A to J, I would have to go use connection object of shard 1, otherwise shard 2, otherwise shard 3. So this is where the logic of quote unquote routing, this is called routing logic, where the request from your user comes in, API server knows where to route the request, which means which connection object to use to make calls to these databases, to one of these databases. Right? This is where you're defining the routing logic at the API server side. Right? This is how sharding works. We'll go detail into sharding in the next video, but you get the overview of sharding. Right? This way what happens is, because now each shard is responsible for 1/3 of the keys. It's not responsible, like one shard is not holding all the keys. So we are literally slashing the load on each database by a factor of 3. By splitting that one database into 3 databases, each handling mutually exclusive subset of data, right? And here I described one very simple way to route it, where your API server knows about existence of all the 3 shards and the routing logic. There are multiple ways to do it, a little advanced, but you'll get the idea that what sharding does, why it is important, and how you can naively implement it. Now, what I would recommend, I would highly recommend you to implement read replicas. Just have 2 databases and in your API server use either of the connection object to fire the query on that particular database. You'd know what sharding is, you'd know how quote unquote read replica is. If you are feeling excited, implement a replication on that. Set up a data node, set up 2 databases, make one as follower of other, whichever database you are picking up. Just Google how to create read replica for, let's say, MySQL. You would get those steps and implement it, right? You would have a time of your life when you do that replication on your own, sharding on your own, API server handling or routing that logic to individual thing. You would have a time of your life implementing it. Like, I would highly recommend you to implement that. And yeah, I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.